Imagine you're trying to schedule classes for a school. You have a list of subjects, a set of classrooms, specific times, and different teachers who can only teach certain subjects at certain times. The goal is to assign each subject to a time slot and a classroom without breaking any rules. This kind of problem is what we call a constraint satisfaction problem, or CSP for short. A constraint satisfaction problem is a type of problem defined by three components: a set of variables, a set of possible values for each variable, and a set of constraints that specify which combinations of values are allowed. The goal is to assign a value to each variable in such a way that all the constraints are satisfied. Let's use a simple example to make this clear. Imagine we have three friends, Alice, Bob, and Charlie, and we want to give each of them a different color for their t-shirt. The available colors are red, green, and blue. The variables in this case are the people. The values are the three colors. The constraint is that no two friends can wear the same color. This is a classic CSP. Assign a color to each person so that everyone has a different one. To solve a CSP, we often use something called backtracking search. This works by assigning values one at a time, checking whether each step violates any constraints. If a constraint is violated, we backtrack and try a different value. It's like trying out options one by one and going back whenever we hit a dead end. Although it sounds simple, this method can be made much more efficient with some smart strategies. One of these strategies is forward checking. Every time we assign a value to a variable, we immediately eliminate that value from the domains of neighboring variables that are affected by the assignment. If any variable ends up with no valid values left, we know that this assignment can't work, and we backtrack earlier. Let's go back to the class scheduling example. Suppose you have 5 subjects: math, English, science, history, and art. Each subject needs a classroom and a time slot, and some teachers can only teach at certain times. On top of that, some classrooms might not be available at specific times, and you don't want 2 classes happening in the same room at the same time. This creates a complex web of variables and constraints. To solve this, each subject becomes a variable. The values are the pairs of time slots and classrooms. The constraints are things like no overlapping times in the same room, each teacher only teaching one class at a time, and so on. A CSP solver will try combinations of these assignments, prune invalid options, and eventually return a valid schedule that satisfies all the constraints, or report that no such schedule is possible. CSPs are not just academic exercises. They're used in many real-world applications. Solving Sudoku puzzles is a CSP. Creating timetables for schools, assigning gates to flights in an airport, even designing integrated circuits, all are examples of constraint satisfaction in action. The power of CSPs is that you don't need to write code that understands how to search for a solution in a specific way. You just define the variables, values, and constraints, and let the algorithm handle the rest. This makes them both elegant and powerful for solving problems that involve a lot of rules and possibilities. In essence, constraint satisfaction problems are about finding a way to make everything fit together without breaking any rules. By thinking in terms of variables, domains, and constraints, we can model a wide range of problems and solve them efficiently using search, heuristics, and propagation techniques.